I would like to let everyone know that this webinar, excuse me, is being recorded. So anybody that wants to download the recorded version afterward will have access to that. Little quick housekeeping here before I hand over to Karsten. If anybody has any questions, please feel free to use the chat functionality of the GoToWebinar, and I will make note of the questions, and then afterwards we'll have the Q&A session, and I will present those to Karsten. So you don't have to wait till the end. Feel free to ask any questions you may have throughout. Without any further ado, I'd like to hand control over to Karsten, and we can begin the webinar. Take it away, Karsten.
Yes, thank you, Paul. Hello, everybody. This is Karsten from the Men&Mice support team, and I will give you an overview over the IETF 94 and the RIPE 71 meetings in November this year. But before we start, please note there is an important Windows DNS security advisory. There is the danger that someone sends specially crafted DNS packages to a Windows DNS server, and that can trigger a parsing error in the code, which could lead to remote code execution, and then an attacker can maybe execute code under a local administrative account there. The fixes are available from Microsoft. And if you go to this URL as they are shown, you will find additional information and the download links. So IETF 94 was in Yokohama beginning of November, and then later on was RIPE 71 in Bucharest. As always with these reports of the meetings, I just made some choices on what stuff to present. I cannot cover everything. There's just too much happening in an IETF meeting or a RIPE meeting. So if you want to have a full overview of the activities, go to the data tracker meetings materials page, the link you find here, and you get a full overview. And there's also recordings of the meetings. So we start with the DNS part from IETF, and this is the list, the first part of the list of the DNS-related RFCs that have been published since the last IETF. And this is a long list this time. There's a lot of stuff going on in the DNS working group, the DNS operation working group, and also there's a lot of outputs in terms of new RFCs. So the latest one, 7720, just came out either today or yesterday, is about the root server, root name server protocol and deployment requirements. It's an update of an older RFC that defines what a root name server in the internet must do and must not do from the protocol perspective, like support TCP, support DNSSEC, and this stuff. There is a special support for the Java protocol there. The RFC about implementing local root zone on the loopback interface, something that we have talked about in one of the previous sessions, is now an RFC. And also after much debate, and the debate isn't over, the second special use top-level domain .onion is available, has been formalized with RFC 7686. It was just in time for the TLS certificates of Onion sites to be not expired. So that was good, but that still sparked an ongoing debate in the IETF what should happen in the future with special use domain names. And this IETF wasn't different here. There was a session on the RFC 6761, which is the RFC that defines the protocol on defining a special use domain name. And this is much under debate currently. Then the DANE RCs have been published. The one for SRV records, and continuing on the next slide, the one for SMTP for email, using the TLSA record to store certificate information in DNS. And the updates and operational guidance RC 7671 also has been published. Then also long in the making and a lot of people waiting for that is the definition of DNS negative trust anchors. This is basically a way to tell a DNS recursive validating resolver that a remote domain that is DNSSEC signed is insecure, or better, should be treated as insecure, because it has some well-known errors which are not an attack. So operators of a validating resolver can put a negative trust anchor in their configuration, and then that domain will be exempted from DNSSEC validation. And the DNS privacy considerations from the DPRIVE working group has also been published. We've spoken about that in the past. And now to some new stuff. The SMIMEA record now have a dedicated DNS record type. It's type 53. There also were a lot of people waiting for that because we already have operators, email service providers, mostly in Europe, that want to go in production with SMIMEA and also OpenPGP key. And for that, they needed to have a resource record type to store the SMIME certificate information in DNS, and that's now possible. Now the documents about SMIMEA and OpenPGP key are still in debate, so there's no RC about that. It's still a draft. But now at least the record types are in the IANA registry, and people can start provisioning their DNS with SMIMEA and OpenPGP keys and test that. And then there was an interesting discussion of whether the resource records in DNS sections have an order. So common knowledge among DNS operators is that the resource records in any DNS section can have any orders, like in the answer section, in the authority section, or in the additional section. But turns out that at least some implementations see it differently. So someone from the audience in Yokohama told that certain Windows DNS servers, they expect the OPT pseudo record as the first record of the additional section. Mike Andrews from ISC mentioned that TSIG and SIG0, they have special requirements for ordering. And someone else mentioned that some DNS resolvers out there, they need the data record and the signatures for that data record to be in order. So when first the signature appears in the data and later on the data record, these kind of resolvers don't validate correctly. So this document wasn't adopted by the working group, but it was an interesting discussion anyway, learning that there are particular implementations and that can lead to subtle errors in DNS, and new stuff appears even after 25 years of working with DNS. So then Paul Waters presented a draft on the management of DS, delegation signer records, and how they can be automated. There is now the CDS and CDNS key RC that allows the automatic provisioning of delegation signer or DNS key records from a zone. Basically, the owner of the zone publishes a new DS or a new DNS key as CDS or CDNS key in his own zone, assigns it with the current key, and the parent authoritative DNS server can then fetch these new data information, validate with the existing DNSSEC keys, and then place it into the parent zones. Now that works when there is already a chain of trust to the zone. This draft talks about how to generate the trust in the first place. So the initial trust, how does the DS record or DNS key record can be trusted when it is published the first time. The draft also talks about how to remove an existing DS record from the parent, and that would be by publishing a CDS or CDNS key with all values set to 0, basically telling the parent that the DS record should be removed and the zone should go insecure. You might have heard that, and we've spoken about that in a previous review, that the root KSK key should be rotated in the future. And one of the problems here with the root KSK rollover is that there's currently no way to measure how many of the DNS resolvers actually have picked up the new root KSK and are updated for future use. So when can the old root KSK be removed? And this new document from Duran Wessels suggests that there should be DNS resolvers should send the key tags of the trust anchors they have, at least for the root, maybe for other trust anchors, with queries, but only if the query type is of type DNS key. So if the resolver is asking for the DNS key, it would then, in the EDN0 part of the request, send a list of all the trust anchor it currently owns. And with that, there's then a feedback loop for the operators of the root server infrastructure, whether sufficient enough resolvers have updated their trust anchor. Now, given that it would take probably a few more months to get this draft through the IETF, and then it needs to be implemented in software, and then that software needs to be deployed. It might be a good idea, but it might be too late then, because maybe the root KSK rollover will start or must start earlier than that. With this idea, also DNS forwarding is tricky, because the different DNS resolvers on the forwarding chain might have different trust anchors. What to do with that? Create a union, create an intersection, or something different. And there are also privacy and security considerations, because then if a DNS resolver sends all the trust anchor key tags to the root zone, the operators of the root zone can then do some data harvesting on what other trust anchors are being used. So this is still in discussion in the IETF, whether this is a good idea. And then Stefan Bortsmeier from AFNIC had two questions about possible new work in the DNS operations working group. First is about should there be, or would it be a good idea to have a DNAME in the root for the .local special use domain. .local is currently either the second or third most popular top-level domain being requested from the root name servers. Of course, the root name servers cannot make any sense of that request, because .local is not delegated in the internet. It's a special use domain. It's only useful in a local network. And the DNAME would then redirect .local into the AS112 servers, which is a special DNS server infrastructure for giving NXDOMAIN answers. AS112 is currently used for example, for private IP address space for the pointer record lookups, or the reverse lookups here, and could be used the same way for .local. And then the second request was about an optimization in DNS resolvers. NXDOMAIN means NXDOMAIN. Currently, most DNS resolvers, they just store they cache the NXDOMAIN information for the particular name they have resolved. So if a DNS resolver learns that example.com is an NXDOMAIN, doesn't exist, and then later on a request for example.com comes in, then the resolver will look in the cache, and it will not find an NX domain for example.com, and will send the request anyway to the authoritative name servers, and will then get an NX domain back. However, the DNS namespace is a tree. So if the parent domain, or one of the parent domains, like example.com, is already non-existent, is an NX domain, then everything below that should also not exist. And a DNS resolver could just build a tree from the data in the cache, look up the data along the tree, and then can just directly answer with NX domain for any new query that falls below a domain that is already marked as NX domain. That would help with queue name minimization, so less exposure to the root name servers and other authoritative name servers. And it could also help with some random queue name attacks, because operators could just inject the base name of the domain being attacked into their caches, and that would stop all the requests for all the random names that are queried as a subdomain of that domain. As Paul Wouters noticed in the meaning, this would break split horizon setups, where and this is especially seen in enterprise networks, where you have internal namespace and internal IP addresses, and you have the external namespace. If you have, so you have two different trees here, not one single tree. And if there's an NX domain, for example, in the external world, in the internet, that doesn't really mean that there is an NX domain in the split horizon case in the internal namespace. But there was some interest in going further with this discussion, so probably Stefan will create a draft for this, and will present it in any of the future IETFs. So going to IPv6 on the IETF, this is the number of RFCs being published for IPv6. There's DHCP Shield, a method of protecting against rook DHCP servers, which is best current practice. There's the DHCP active lease query, now being an RFC, IPv6 over Bluetooth, low energy, and IPv6 support for gray tunnels, generic router encapsulation. Interesting new work from the IPv6 operations working group. Comcast started a public Wi-Fi trial on their extensive Wi-Fi network they have across the US. And what they do is they give every device a /64 prefix. So every device doesn't get a single IPv6 address. Every device gets a full network of IPv6 addresses. And there are multiple reasons for that. Especially in Wi-Fi, there are some negative side effects, let's say that way, with neighborhoods discovery and duplicate address detection and so on. So if multiple devices in a Wi-Fi are in the same prefix, in the same network, they have to do certain polling of the base station to figure out what is the status of neighborhood discovery. And that polling drowns the battery, which is bad for mobile devices. Giving every device a /64 solves this problem, and also it provides isolation between devices, because the device is then the only device in that network that cannot reach any other device other than through routing. So that nicely is a property that someone wants to have in a public Wi-Fi, so that the users of that public Wi-Fi cannot see each other. And that was an interesting discussion on the IPv6 design choices. IPv6 design choices is an internet draft about various design choices that can be made when starting IPv6 deployment. And the change from last IETF is now that enterprise IPv6 networks are in scope of the document. Previously they weren't. And the authors have listed in the document options for enterprises today to get IP address space. And the three options are there to have provider independent address space, which has certain positive effects, but also has the negatives that it's usually only available for larger organizations, for the Googles and Facebooks and bigger telcos to have a own provider independent address space. The other options are to use provider aggregatable PA address space and unique local addresses internally. So having a mix of local names, local IP addresses, private IP addresses, and official IP addresses from one or more ISPs. And the third one, and that was the most controversial, was about using unique local addresses internally and then do NPT, which is a kind of NUT, network port translation 6 to 6, so translating IPv6 to IPv6, but changing the IP addresses, which would be very similar to what we have today in many networks with NUT 4.4. That is the network address translation between NPT is network prefix translation, not port translation, prefix translation. So the prefix will be replaced, but not the host identifier. However, there was a long discussion on whether it is appropriate to have ULA and network prefix translation 6.6 in such a document without having a big red sign on that is actually a very bad idea. This will probably now go into the document. However, the consensus was also that all options for enterprises today have issues. There's no clear winner, so there's nothing that is a recommended option here. And the IETF is working on solutions, mostly in the space of source-based routing, but these solutions aren't available. So the aim of the authors of this document is to document what's currently available and give guidance what to choose here. And then there was an interesting presentation from Akamai about their work on classifying the IP addresses they see on their content delivery network. So they made an effort to classify the IPv6 addresses they see by a temporal matrix, that is how long they see the same IPv6 addresses and prefixes, and also about the location, that is in what prefixes, with networks are the IPv6 addresses being seen. And interesting takeaways, at least for me, from this presentation was that Akamai doesn't see they don't see EUI48 host identifiers, that is IPv6 addresses created out of MAC addresses, hardware addresses, which is good for privacy. And they see more than 90% of the IPv6 addresses they see are privacy addresses, the really random host identifiers. So the privacy extensions are really out there, and every client operating system is implementing them correctly. A nice benefit of the work they did is that with the work they have now a map of the IPv6 address space in use, quite good map. So they know which areas of IPv6 are being used and which are just allocated but not being in use. Akamai makes the data sets available, not all of them, but at least 2 data sets from March 2014 and May 2014. The presentation has the information where to obtain the data set. Also nice to see here in the graph that there's no significant Teredo or isotype, a little bit 6-to-4 traffic coming there, but most traffic is real native IPv6 that Akamai is seeing. So, and that was the part about the IETF, and now we come to RIPE 71. Bucharest. And Joa Damas gave a presentation about the study he made with a medium-sized ISP. That medium-sized ISP has DNS resolvers, roughly between 200 and 400 queries per second, so not much, but still a good number. And he did a study on the impact of DNS over TCP on from DNS resolver view. And the takeaway from his presentation is that TCP timeout management is important. So if you operate a DNS server with a lot of TCP connections, you might want to tweak the kernel parameters of the TCP IP stack so that the operating system doesn't wait for a TCP connection timeout too long, because that could just use up all the resources on the DNS server's operating system. So, because DNS is such a quick protocol, usually we just have a short-lived connection, and so TCP DNS connection should be recycled very aggressively. He also found that the message sizes due to DNSSEC is mostly not a problem. Most DNSSEC answers he's seen were below the Ethernet MTU, that is lower than 1,500 byte. So they could be carried over UDP, no fragmentation needed, and also no need to switch over to TCP. And he looked on the issue of connection reuse. Connection reuse means that the DNS server keeps a connection to a remote authoritative DNS server open after the first query, on the idea that there might be more queries are coming. And he found out that for regular DNS resolvers that doesn't make sense, because there's not enough queries to the same authoritative name servers in a short amount of time, so that connection reuse would be beneficial. An exception are specially used DNS resolvers, for example, the DNS resolver that is explicitly configured as the resolver for one or more mail servers, because mail servers have a lot of queries for the same domains. Think about spam prevention, spam house, DNS-based blacklists. These requests go always to the same domain and almost always to the same authoritative server. So keeping the connection open, the TCP connection open to these servers would make sense. Then Jaap Akkerhuis presented on the progress on preparing for the root zone KSK rollover. The root zone KSK rollover will use RC5011 protocol. That is, they will publish the new KSK, sign it with the old KSK, wait until a sufficient number of resolvers have picked up the new KSK, and then switch over and retire the old key signing key. That whole process will probably take about 6 to 9 months, so no need to be alert now. The plan is not yet final, it's not finished, it's just little progress being made. And when the final plan will be published, we will have an extra webinar on that topic, and we will explain for DNS resolver operators what they should do to make sure that they pick up the new KSK. There is a new announce mailing list. You see the URL here on the slide. If you want to be informed about any news about the root DNSSEC rollover, please subscribe to this mailing list. And then Willem Torup from NLNet Labs had an interesting presentation about a get DNS NS switch module that can replace the default operating system stub resolver. This is to solve multiple problems. One is that the signaling in DNSSEC between a validating resolver and the application is not there. So if a validating resolver denies the DNS data because DNSSEC validation fails, the application and the stub resolver don't know what is failing and whether that failure is a DNSSEC failure or is a just generic DNS problem. With the get DNS NSSwitch module. Basically, you configure in your nsswitch.conf on a Unix machine the new module, and that new module will take over the DNS stub resolver function, and it will do more than a normal stub resolver. It will keep state. There's a get DNS daemon running, and it basically works then like a full validating resolver, but in kind of a stub mode. It uses the configured resolver from etc resolve.conf. It has a configuration web UI, and with a tricky hack, if there is a DNSSEC validation error and the request is coming from a known web browser, that is the module is checking the process name, and when the process name, for example, is Firefox, it knows, oh, this query was coming from the Firefox web browser, so that is an application that can actually display a web page. Then it will rewrite the serve file into an actually a record answer that is pointing to the loopback interface, so it's giving out the loopback address, and on the loopback address there is then the get DNS daemon running, get a DNS daemon running, that is displaying then the sense code for the failure. Why is the data not delivered? What is the DNSSEC problem? For example, here it was a bogus DNS query. The code, unfortunately, is only proof of concept. It's not production-ready code, but it's available as open source. You can download that and play around. And I really would like to see this being adopted and maybe polished by some of the maybe Linux distribution vendors or someone else to have that as an option in a Unix operating system. And someone from SIDN came to the mic and was explaining that might be Yelta, not sure, that SIDN is working on a similar signaling with Unbound, and I'm also looking forward to see that. And then there was a presentation from CZNIC about GeoIP implementations in open source DNS resolvers today. Motivation was that the not DNS team, they are implementing GeoIP. What is GeoIP? Basically, you have kind of an access control list in your DNS server, and based on the location of a request, you give out different data. So that is maybe similar to views in bind, but it's not based on the query or IP address itself, but it's based on the geolocation information in some geolocation database behind the IP address. So if a query is coming from Europe, you might give the IP address of your European data centers. If the request is coming from Asia, you're giving the IP address of your Asian data center back. And there are different implementations already available in different DNS servers. For example, Bind has an implementation starting in Bind 9.10. PowerDNS has an implementation, and there are certain special purpose GeoIP DNS servers out there. Also, this presentation discusses the eDNS client ID subnet option, which is a subnet option that will allow the authoritative server to learn where the original client is actually being located. Because if the client is using a resolver that is maybe a public large centralized resolver like the Google DNS, it might not be obvious where the actual query is coming from. That again also is available in PowerDNS today. It will be in not DNS, and there was a remark on the mic from Vicky Risk of IC that the client ID subnet will be in the upcoming Bind 9.11 version. Another presentation from CZNIC from Andre Zure was about the Turris router. Turris router is a project by CZNIC to get data about attacks in the internet on home users, on scans, on all kinds of attacks. And Synthetnik first produced some 1,000 devices and gave them out for almost free to people in the Czech Republic. And the motivation here was to have a probe for security research. For example, these devices can run honeypots for Telnet and SSH, which are then tunneled to central servers. So the honeypots are not actually running on the router. The routers have ports open for Telnet and SSH. And if someone connects, that connect will be tunneled to central servers in the Synthetnik data centers and will be analyzed there. These routers were quite powerful, and they have container virtualization for local applications. So the owners of the router can install their own cloud installation, run their own mail servers, maybe have a web server there. And it's all based on OpenWRT Linux. And on the website Turris, there's all kinds of statistical information about what they have found out. And because a lot of people have asked, oh, this is a really, really nice hardware, I would like to have one home. Can we buy one? Synthetnik started a crowdfunding initiative for what's called the Turris Omnia router, which is basically a very similar router, different hardware, but very similar. It's a powerful home router. It has VLAN support. It has a fiber optic plug there, a hardware random number generator. It runs the GNOT resolver and many, many more. And they asked for $100,000 as the goal for starting production of these routers, and they surpassed that number in the first day after 21 hours. And it's still open. If you are searching for a nice Christmas present, this might be. The Turris Omnia router can be used as a security probe, but it's actually an opt-in, so you don't have to participate in the research that Synthetnik is doing. You can just buy this device, contribute to the crowdfunding, and just run it as your home router. Then Andres Kaletka from CERNET presented some measurements that he did on the use of transport layer security between mail servers. Was motivated by a presentation that I did together with Patrick Curter last RIPE meeting. And in the video, he presents what he found. How many of the domains being used for mail servers already have DNSSEC. It's like you see here on the picture, is roughly a quarter, a little bit less than a quarter. And how many of these already deploy DANE, which is currently roughly 1%. But there are some big players in there, so the percentage number by domain is maybe not really telling the right story, because it might be better to just count the number of mails that are secured by these TLSA's deployments. And the takeaway here is there's no secure email without DNSSEC. So if you are in the email business, if you run a mail server and you don't run DNSSEC, look deeper and might consider deploying DNSSEC. Randy Bush did a presentation on the automatic certificate issuance. That is the Let's Encrypt certification authority. It's a joint work of the Linux Foundation, Mozilla, the Electronic Frontier Foundation, and other interest parties in the internet. They created a protocol, the ACME protocol, the Automatic Certificate Management Engine protocol. That protocol can be used with any certification authority. It's not specific to Let's Encrypt, but Let's Encrypt is the first certification authority that makes use of this. Basically, Let's Encrypt is a certification authority that gives you TLS certificates, SSL certificates, for free. There's no payment here, and the idea is to have widespread encryption in internet protocols that requires TLS certificates. So by making it free, they hope to foster the use of TLS. In the talk, Randy Bush had some critics on the Python Acme client that is delivered from Let's Encrypt. And because of that, here I have two links to alternative clients. There's one bash shell script and a tiny Python script, which is only 200 lines, so it can be read and maybe understood by in finite amount of time. Also interesting, there is a statistics page from Let's Encrypt where you can see how many certificates have been issued, certificates by country, how many revocations, and so on. That's let'sencrypt.org/stats. I already have several Let's Encrypt certificates. I must say it works very well. And if you haven't secured your service with certificates and TLS so far, please consider it. Then Jeff Houston did one of his talks based on research he did using the Google Ad networks, and this time he looked at the mobile internet. From his research, he sees that mobile devices currently make up 40% of the hosts in the internet, and this number is going up while the desktops and laptops are on the decline. These are the blue line in the chart you see here on the slide is the number of laptop and desktops seen in the internet, and the green line is the number of mobile devices, of mostly phones, and the pink line is tablet devices, and the orange line is gaming consoles. So gaming consoles don't play a role. Tablets and mostly smartphones, they play a big role. His observation is that the mobile world is quite different from the internet that we know of, because the mobile world is built on network address translation and carrier grade networks, and there is it's a highly controlled environment, and there is no end-to-end connectivity in there, and there might be a danger for the internet on the longer run, because it will be less end-to-end, and new applications might not work. So he also looked at the on IPv6 in the mobile device market, and that looks very promising here, because running dual stack costs double in the mobile world, because certain licenses have to be paid by used IP addresses on the middle boxes. So carriers try to not go dual stack, but instead switch to IPv6 completely and provide IPv4 as a service by tunneling and similar things. Then on a different talk, Jeff Houston looked at IPv6 performance and TCP/v6 reliability. And in 2011, he did a research similar to that, and he found that IPv6 had a 40% failure rate, which is quite high, and that was mostly due to tunnels, because at that point of time there was not so much native IPv6. And this number has gone down to 4.1%. Failure rate, which is also due to tunnels. But if we take out the tunnels, it's still 2% failure rate without the tunnels, which is quite high compared to IPv4, which has a 0.2% failure rate overall. So IPv6 failure rate is getting better, but it's still not good. Work needs to be done there. And also then he looked whether connections over IPv6 are faster than connection over IPv4 for TCP unicast connections, and he found out that there's hardly a difference. Roughly 48% of the connections, connection time IPv6 is faster, 52% of the time IPv4 is still faster. And that might be still, the difference here might be still because of the tunneling. So the difference towards IPv4 might be because IPv6 through tunneling is, of course, or might be slower than native. And Jeff Houston's colleague Michael Abramson did a presentation on what can be seen from the statistics of IPv6 addresses and what kind of technology is being deployed in mobile markets. First off, the Google Ad network they used for their measurements had to switch from Flash to HTML5 in September this year. This is because Google is shutting down all Flash. And this had the nice side effect that now more mobile devices are in the data sets, because mobile devices traditionally didn't have Flash, especially the Apple devices don't have Flash. And now with HTML5, a lot more of these devices appear in the data sets. And for the mobile networks, there are basically two ways to operate IPv6 there. One is to run dual stack IPv6 and IPv4 at the same time. Another one is to use 464 XLAT, where IPv4 is tunneled over IPv6. So the carrier network is IPv6 and then is translated back to IPv4 on the edge. 464 XLAT is supported in Android, but it's not supported in the iOS devices. So with the amount of 464 XLAT in the request, you can see no, the other way around. The amount of iOS devices in IPv6 data, you can see whether the carrier has 464 XLAT deployed or has dual stack deployment. And here's a picture from the T-Mobile network. And the green line is all the Android phones connecting, and the yellow line below there is the iOS phones connecting over IPv6, and we see no iOS over IPv6, but we see Android, and that is usually a clear sign that there's 464 XLAT in the network being used. He also found out that 25% of devices in the US are currently IPv6 capable, that is, they can use IPv6 if they want to. So that concludes my today's review of the RIPE 71 and IETF 94 report. Again, this was just an excerpt from all the talks and good stuff that happened there. It was just my own choice what to pick out. There was a lot more. If you're interested to see everything, please go to the archive sites of the IETF and the RIPE meeting, and you can find all the presentations there. There's a lot of good stuff there. Our next webinar is already next week, Wednesday, December 16th, and there we will talk about DNS tab, which is a new technology for recursive DNS servers to get data out of the DNS server that is data similar to query logging, but without the performance negative performance impact on the server here. And we will talk about how DNS tab is implemented, which DNS servers currently have a DNS tab implementation, and I will show how to use the hooks and how to analyze the DNS tab data stream. As always, you can sign up on the Men&Mice webinar page for that. And now let's look at some questions if we have any.
It looks like we haven't received any questions, Carsten, but I would like to remind everyone that if you do have a question afterwards, if something occurs to you, you could feel free to email those questions to us. We'll be happy to answer them. And also as a reminder, this webinar has been recorded, and like Carsten said, will be out in the archives and accessible to everybody that registered.
Okay, thank you.
So thank you all for attending, and we look forward to seeing you on the 16th for our next webinar.
Next week. Have a good weekend then.
Take care, everyone.